Welcome back to my garage. What you see in front of me here is a selection of crap. It's a selection of parts which when assembled will constitute the brute force concept engine revision 1, which is what we're going back to now. I'll explain in detail and start a dry assembly where I can explain, so that everybody who wasn't watching, or everybody who was watching, and all the new viewers who wasn't watching those like 3-4 years ago or so, when this was built and was running. I'm gonna do a dry assembly to make sure we have all the parts. I know there's some stuff missing, and I'll explain later. First, you know how I'm trying to do things better. Well, I'm always trying to do things better, but I'm trying to improve upon my process. Not so much free jazz, and if it's free jazz, at least take some like 5-minute breaks and think about what you're going to do, and think of possible errors that can pop up and stuff. So I took a trip to Mitutoyo, Stockholm, and I brought the cylinder. This cylinder, or actually not this, but the same cylinder, the other one I cast, and a selection of jets. And what we did there was first of all we measured the roundness of the bore and the perpendicularity and the surface roughness and stuff of the cylinder, to see how well my milling and everything and honing and all that how good that is. And also we measured these jets precisely, because I've always been uncertain about jet sizes. If a 130 jet, is it really a 130? And they're probably not. Like, there's variations between. So if you have a selection of 10 130 jets, then there's probably big variations. But at least now I've measured these, and every single one of them was about 0.2 millimeters over what they said they were supposed to be. Well, like, no, 0.0. I shouldn't have said that. That's something you should see later in the actual, when we're doing the measuring. So forget I said that. I've spent many hours trying to edit down the footage, so there's lots more than what you're going to see now. And I'm sorry for like bad introduction and probably all that. There's a couple of things going on here. There's the crippling social anxiety, which I'm really good at hiding, but it's definitely a problem, and I'm more aware of it now than I've ever been. And also there's the imposter syndrome, because I'm pretty much bringing absolute chaos to absolute precision at Mitutoyo. So yeah.
Hi, I'm Dory. I work here in Mitutoyo as an application engineer for measurements, and I work with both the CMM and the VMMs. CMM is measuring with Pro.
So this is a CMM machine.
And the meaning with that is that we are measuring with the stylus, so with the Pro, which are having different dimensions. We have, of course, also possibilities to select other devices like laser scanning and optic devices and surface roughness probes.
So there's 1.2.
So this is a starting error of 1.2 microns.
Yeah, 1.2 microns.
And we have machines down to like
0.28.
0.28 microns. Yeah, that's pretty accurate.
That's very accurate. So wherever I start in the space of this meshing area,
Yeah.
I have an uncertainty of 1.6 microns.
Oh, okay. Yeah.
Or a meshing starting error.
Oh, okay.
Results,
The
which
results.
is coming out, yeah. And I of course don't know what are the specific tolerances, so
No, exactly.
it might not be correct, but I anyway saw that the cylindricity here is 25 microns, and I wonder, you can see that the average diameter is just half a micron.
So
Under
that's
40, so probably that was good.
yeah. That was my. That's after honing and measuring with. So my measurements were perfect.
It
'Cause
looks
I think,
like it.
Yeah, I measured it to 39.996, I think. So
Yeah.
that's not far off the. I think why it's you said 25 microns out of round.
Yes.
Yeah, and I think that's because of the super. So people that has been watching will know that there was a far too tight press fit here, and the whole thing bulged, and I think that's the problem, that there's so much tension still. So
Yeah, I'm sure it's the tension in that case.
Yeah.
And I can see you managed very well, because I see it's welded, so you see that the perpendicularity is extremely good.
it is.
Yeah, so it really is very, very good.
So the bore
Value.
in relation to the bore
yeah,
in relation to this surface is
yes,
really
it's
good.
perfect.
Oh, because I thought it wouldn't be, but it is. So
Yeah.
that's great news.
So that's very nice.
Yeah, you told me last time that there's some of the most accurate machines you have or you're producing. There's restrictions on them, so we can't export to whatever country you
Yes,
want.
that's true. So if they're the higher accuracy machines are export controlled.
Yeah,
So we can't sell them to different countries and everything. So if we sell one of these machines, we have to go very rigorous testings and interviews and do a lot of investigation before we can actually sell them. But that's only for the highest,
the super high
the
precision
super
stuff.
accurate machines.
And that's
right?
because that's to prevent the wrong people from producing accurate enough stuff to make bombs and
Yes, exactly.
stuff.
So that's
yeah.
exactly why.
So, but it's kind of funny that there's restrictions on measuring equipment.
Yeah, most people don't know.
No.
But there are some products that's so accurate that we're not allowed to sell them
Yeah.
freely on the market.
Because the machine I'm not sure. So this one has this box on it, and that was like a
Yes, that's a movement sensor.
movement sensor. So if that gets triggered, then there's all hell breaks loose.
Not maybe all hell breaks loose, but the machines actually stop working.
Yeah.
We have to send out a technician to unlock the machine. So
Yeah.
most of the machines do have this, and this is just so we can keep track on the location of the machines.
Yeah, exactly. Yeah.
So if we have a restricted machine somewhere, it needs to be. You can't move it
No,
basically,
no,
without
because,
us knowing about it.
No, exactly. So this is your calibration room, calibration area.
Yes, this is the calibration laboratory at Emot Scandinavia, and this is a very controlled environment. As we all know, metal expands and contracts depending on temperature. So in here we have a steady 20 degrees all the time. We have 8 temperature sensors and I don't know, like 3 or 4 humidity sensors.
In different heights,
Yes.
and in 2 different locations in the room.
Yes, exactly.
So
and we have a very big HVAC system up here that controls the environment in here. And it circulates about 6,500 cubics of air every hour.
yeah, so
And we also have to be very careful about draft.
yes,
So we have these socks in the ceiling. And so you don't get draft in here.
so a little bit more controlled than my garage, probably.
Yes. So in our world, temperature is very critical.
Yeah.
So as you will see with the coordinate measuring machines, the CMM machines later, they are also temperature compensated.
Yeah.
So the machine can compensate for both a bit of room temperature and the workpiece. So you can actually put sensors on the workpiece, so you can compensate for the thermal expansion of the workpiece.
On the workpiece.
On the go.
On the go. Oh.
Yeah. So basically, one of the services we offer is calibration.
Yeah.
So what we usually say is that to measure is to compare.
Compare, yeah.
This vernier caliper has no clue what a millimeter is.
No.
It has no intelligence or anything. The only reason why it can measure so well is because it's been compared.
Yeah.
Right? And of course it needs to be manufactured at very high tolerances. And
Yeah.
So what we do is actually we compare instruments. This is what we're talking about when we're talking about calibration. So we compare this to a known standard.
Exactly.
And that standard has also been compared to another machine that's even more accurate.
Exactly.
So when you get a caliper or an instrument, you usually get a little note. It's a certificate of inspection.
Yeah.
Don't throw this away. This is a very important part of the measuring process because it gives you traceability.
Yeah, exactly.
You can actually trace the serial number and the certificate to another certificate or another machine all the way back to like an international standard.
Exactly.
Yeah.
So
that's why it's so important to keep track of your papers when you buy measuring equipment.
Yeah.
And also have a well-built quality system for your business or enterprise to keep track of these things.
Yeah, I'll keep that in mind.
We usually talk about the calibration hierarchy. So in the bottom of this hierarchy you have the end product or the measuring tools that you use to produce the end product.
Yeah.
And then one step up you have like your setting rings, like these, or the gauge blocks.
Yeah.
And above that you have this machine, this gauge blocks tester.
Okay, so that's a gauge block calibrator.
Yes, it's a comparator.
Comparator, yeah. So
So you actually put two gauge blocks in there, and you compare those two gauge blocks.
Yeah.
So we get the customer's gauge block, and we have our own gauge block that we've tested.
You've tested, and you have some really high precision gauge blocks here.
Yes, and these are made of ceramics.
Yeah. And why is ceramic versus that for durability? So they don't get scratched as easy? Is that or is it thermal expansion, or why ceramic and not metal?
There are a few reasons for it actually. The thermal expansion is quite similar to the metallic ones.
Oh, okay.
But as you said, they're very scratch resistant. They're up like 10 times more scratch resistant than steel gauge blocks. And they also don't age as much.
Oh, so
they're form stable. So steel gauge blocks, actually most people don't know this, but it's kind of like wood. It's a living material.
Yeah, exactly.
So you get dimensional changes over time. So even if you don't use them so much,
still they will change dimensions. And these will not so much.
No, these are much more form stable over time. So durability and form stability. And if you drop one of these, they crack. If you drop a steel one, they deform.
Yeah, exactly.
So you can actually fix, if you drop a steel gauge block, they will usually get dented at the corners.
Yeah.
But these will
just chip off a piece. Yeah.
So that's the main difference.
And this is the set you're using for comparing to customer gauge blocks.
Yes, that's correct.
Yeah. Nice. And this has to be done in absolute silence.
No. What we have to do is actually the small tools that comes in there. And by small tools, I mean all the measuring equipment you can have.
In your hold in your hands.
Yes. So when we talk about small tools, this is what we mean.
Yeah.
So These needs to be here at least 24 hours to stabilize before we actually do the calibration process.
Yeah, because otherwise they'll just keep on changing and...
Yes, so it's very important for us to... And it's the same thing with our service technicians when they work on the machines out in the field.
Yeah.
We have to actually send or be there at least 24 hours before and leave the tools that we use to calibrate the machines.
And let everything acclimatize.
Acclimatize.
Yeah.
I don't know.
Acclimatize.
But so they get stable. So they need to stabilize in the environment they're going to measure.
Yeah, exactly.
So what he's doing now is checking the parallelism of the surfaces, and he's also checking the surfaces for defects.
Okay.
I don't know if you can see this, but at an angle you can see there's lines in different colors.
Yeah.
That's how you can
okay.
see.
So the camera isn't picking it up, but there's...
Every line I think is 0.32 microns
Okay.
deviation.
And I have to turn this a little bit and move it because there could be some air in between.
Yeah, exactly. So you
I
have to push out
get
all the...
rid of that.
Yeah.
So this is what you end up with, calibration certificates.
Yeah.
So you see the deviation, and you have traceability to us,
Yeah.
and to the next, the gauge block set that we use to do the calibration.
Yeah, exactly.
Alla är bra för ja.
Yeah.
So this is a surface roughness testers. The first and the most common way to measure this is with a handheld unit like this, and you have basically two types of systems. You have a skidded system like this one. You have a skid and a small stylus in a hole that tracks the surface, and you get the profile of that surface.
Yeah, yeah.
And on that profile you can then do different calculations and evaluate with different parameters. Right?
Exactly.
So, but this system is limited because the reference plane is by the skid. So
Yeah.
the skid is the reference plane.
Exactly.
So that means if you're trying to measure the surface roughness of a radius, you can't compensate for the form.
No, exactly.
Right.
So,
So then we have another kind of system that's a skidless system, where the reference plane is in the machine.
yeah.
We can try to measure the cylinder with this, but as you see here, there's problem with the accessibility. I can't put it in here.
Oh.
So this unit is actually detachable,
Yeah.
and you can put an extension cord on it.
Yeah.
And then you can mount it in like a height gauge like this,
Yeah.
and then you can access the...
Access smaller features.
Yes, exactly.
Yeah.
But this is a very portable and easy system. So you just press power, start it, and then you have a specimen here. So if I want to measure this surface, I just put it on the surface like this, press start, and then it tracks the surface.
Yeah.
It even draws the profile in real time.
Yeah. Cool.
So we have a lot of parameters. We can talk about this for hours, but
Yeah.
the most common one is RA.
Yeah. All right. Roughness average.
Yes, exactly.
Yeah.
So this is the actual profile of your cylinder.
Yeah. This is a machine without the
Without the
skid.
skid. Yeah. So this is the entry model for the skidless measurement.
Yeah.
And here you have the reference plane inside the machine. You don't have a skid that travels over the surface.
No, exactly.
So this will also allow you to get more accessibility But you can also compensate for different form features, like a curvature or a valley or something like that.
Yeah.
And one other benefit with this system is that you can actually do a lot of different kinds of styluses. So you can access in different hard to reach areas, small diameters, and hard to reach stuff.
Yeah, exactly. Why is it traveling down like that? Is that
Because it's leaning.
Oh, okay.
I haven't compensated for the lean.
Yeah, so that's not.
But now it's compensated it like compensated the curve for the lean.
Yeah.
So this is the actual. This is an exaggeration of your
of
the profile of your actual surface.
Yeah. Interesting. I'll have to read up on the numbers and see if this is good or if I have to do something about it. Change the process. A huge thank you to Mitutoyo and Thomas and Doron for helping me out, and also a huge thank for this new 3-point micrometer, and more importantly, actually, this 50 to 75 millimeter micrometer, which will make me able to accurately set my bore gauge to larger diameters than 50 millimeters, which was my maximum before. And actually measure holes larger than 50, and you saw what problems arose from not being able to do that earlier with super tight press fits and deformed cylinder and all that, leaking cylinder. I also got some information about reading surface roughness here, cause and Thomas also sent me a nice PDF of like a study of cylinder roughness for best oil retention and stuff. So I'm going to study that and also study this and decipher the results from the roughness measurements and see if I need to change my process. Actually, it looks like I'm pretty good already by chance. So the brute force concept engine. Let's just start that dry assembly and I'll explain along the way. So first up, we're gonna start with the blower itself. So this is an AMR 300 Roots supercharger. It displaces 300 cc's of air per revolution. Earlier I ran this I ran a 48 tooth sprocket on the blower and a 22 tooth sprocket on the engine. So like a little bit less than 2 to 1. 2 revolutions of the crank for 1 revolution of this. I'm going to machine a 24 tooth pulley, and in that way we'll have a perfect 2 to 1 ratio. And this means, because this is a 2-lobe blower, and in that way we can take advantage of the pulsing of this. We can actually have the pulse arrive exactly when when we want it to. And that is when the transfers are open. I think I'll have to assemble the cases first to get this mounted. So this is the super simple case of this engine. And it's you might notice there are no transfer ports here. This is just a clearance hole for the cylinder skirt. And the inside has 2 outlets, 1 on each side and 1 inlet on the bottom. And there's plenty of room around the crank in here. It's a plenum and the crank just happens to be inside of that plenum. That's all. And that's to be able to oil the crank without creating some super fancy pressure oiling system, and I've talked about that before. So let's assemble this and go from there. The press fit for the bearings weren't tight enough. We're going to use retaining compound to come final assembly. Because this is just a sliding fit now. This piece connects the blower directly to the plenum / crankcase. And the only reason this is possible is because we're running methanol and nitromethane before the blower, so substantially cooling the mixture. Otherwise this would be really problematic because of all the heat created by that root blower being run far outside its pressure. It's a happy pressure area. This is an outlet for a backfire slash pressure regulation valve. Actually a wastegate. Studs are a little bit bent. So what's going on here? The blower is pulsing 150 cc's of air for every crank revolution. So in theory we should have 2 bars of pressure in here, as this is a 50 cc cylinder. Of course there's some like overlap and stuff, but so that's the supercharging part. And this is the plenum. And then you have the intake runners, and in here there's supposed to be reed valves. It was run with reed valves. We had some trouble with the reed valves. Here's the liner in this cylinder, and this is an exhaust port and this is a transfer port, and you can see how there's no height difference, almost no height difference. There's just a slight bit of the exhaust port is just a slight bit higher. And the theory here, or which actually works in practice also, so this works. But the whole thing is the exhaust port opens, and there's a slight amount of time where some of the pressure is allowed to escape out the exhaust port. And then the transfer ports open, but the flow is prohibited by these reed valves sitting here. And that works, even though you'd think the reeds would die immediately. But it works, at least for some time. I'll show you what the problem is. And the reason for doing this is this creates variable transfer timing, so that as long as there's higher pressure in the crankcase versus in the cylinder, the transfers are open, even though there's a slight restriction from the reed valves. But as long as there's higher pressure down here in the intake system versus in the cylinder, the transfers are open. So at low RPM, you'll have like very little blowdown and then a huge transfer time. And at higher RPM, blowdown gets larger because it's needed, and transfer time is smaller because reed valves. And it works. But first of all, it seems like every fiber reed I've encountered so far at least, softens when exposed to methanol and nitromethane for an extended period of time. So this isn't immediately apparent, but after it's been sitting in with the fumes and stuff, this will soften somewhat. And they'll go back to their normal stiffness after being aerated for some set period of time. So that's not really a big problem. It just means that this has to be, like, the reeds has to be taken out and dried between runs. So not really a problem. You can see one of them here that has broken because, and that's the thing, I'm not sure if they break because they get softer and then this happens. So the bridge that was supposed to sit here has broken, and the reeds have been like pushed in the middle here. And this is from the combustion forces, because this doesn't happen in normal reed operation. It's happened in these two, and also one of these V-force reeds, where you can't see it, but one of the inner legs here are broken. I don't think the reeds will break as long as there's a bridge there. We'll have to make that bridge really tough. And as you can see here, it's just a tiny thin piece. Same thing goes here, just some thin pieces, because it doesn't have to be more substantial in where you normally see reeds, in intake systems, or in normal intake systems. So what I'm going to do is I'm going to machine some kind of a new reed cage, but run a bridge in the middle that is connected on both sides, so that it's much more supported and maybe a little bit thicker. The reed cages break, not the reeds. Well, the reeds break, but I think they break after the cage has broken. And it might be we have to run metal reeds, but for testing at least, we'll try fiber reeds first, because broken metal reeds are much worse than a broken fiber reed. This is the other part of the equation, a rotary exhaust valve. This shuts off the exhaust duct at bottom dead center. And this is what makes this engine capable, together with the super high transfers with the reed valves in there, makes it capable of continuing to build pressure in the cylinder after the exhaust duct is closed. Because in a normal two-stroke, the exhaust port closes after the transfer ports. So the exhaust port is still open when the transfer port closes, and thereby you can't build more pressure. There's more though, but not for now. But well, I'll explain a tiny fraction of it. If we install a two-stroke pipe, normal two-stroke pipe, onto this with the rotary valve in there, it wouldn't do us much good, because the supercharging from the exhaust this is a tangent, I know, but so something like this wouldn't do us much good here, because the supercharging effect from this pushing mixture back into the cylinder, supercharging it wouldn't work, because the duct is closed. So what I'm thinking, because a proper two-stroke pipe can actually, like, you can have a pressure differential, the pipe versus the cylinder, of like 3 bars. So what I'm thinking, not for now, I'm saying is not for now, because we're trying to stay on track here, but what I'm thinking is we have this close off at bottom dead center, but then there's a hole here which opens just before the piston closes the exhaust port, and we can run a normal two-stroke exhaust and have that returning pulse actually further increase pressure in here, even more than the supercharger can do. That's something to think about. Has been used as a pressure dropping device, or an overflow valve to dump excess pressure. And that was at least, I'm not sure it's necessary in the 2-to-1 configuration. It definitely was necessary in when I started off with this engine running 1-to-1, so 300 cc into 50 cc, and obviously that was a problem. The problem was it was leaking out of every pore, and that was well, it didn't help that I used all these nice fancy parts in 3D printed carbon fiber nylon, which are airtight and stuff. The problem is it's impossible to get them to seal, because when you clamp them down, they're soft enough to deform and bow in the middle. And I tried with O-rings and stuff, but it's just too much hassle to well, this didn't leak. So the thing down here was originally 3D printed. I replaced it just because I didn't want to risk a leak with this, but so 3D printed carbon fiber nylon is really great stuff, but as long as you can get it to clamp down properly, it needs to be probably like run this and some aluminium backing of sorts, which kind of defeats the, well, doesn't really defeat the purpose, because you can make really intricate stuff like this. So this was meant for this. Now it's coming out of this piece. So what do we need here? We need to, I've got pulleys to drive this. I've got this pulley, which is the same as this one. Needs to be mounted here. And I'm going to machine a 24 tooth sprocket. Fuck. So that we can, so it'll run proper 2-to-1 reduction to the supercharger. So I'll have to machine something that will have, so that I can press this onto it and fasten the whole assembly to the crank here. I'll probably reuse this because it has the taper in it already. Reuse this and make something that is press fit onto here. I'm gonna get to work. So in the next video you'll I can't promise this will be running, but we'll be very close to it running, I think. I'm not sure if this is the end of the video. Let's see if I'm just gonna edit tomorrow or start working or have something more to say about this. Well, this is actually, well, this has the reinforcement in there. This is reinforced. The CR85 reeds are, the bridges aren't unsupported like in these. And that's makes a huge difference. So maybe I'll just get, maybe we'll just start with these. Means I'll have to somehow chuck this up in the mill and machine this out to fit this. Let's buy another one of these and machine this so these fit and go from there. Anyways, this might be the end or not. For now, not the definite end.